One, two, three. Okay. Hi, everybody. As you might have already heard, my name is Alex, and I would like to talk today about fearless deploys on Friday evening. But before that, I want to understand the composition of the audience today. Who is a developer here? Raise your hand. Okay, majority, obviously. Developer conference. Who is a, product manager, product owner? A little bit. Cool. Who is maybe a QA or tester? Okay, one person. And who is DevOps? A few DevOps engineers. Cool. Anybody else? Any professions I haven't noted? Student? Okay, and what you're a student for? What you're studying? Computer science. Want to be a developer or somebody else? Developer. Okay, so remember the things from this talk. They'll be very useful to you. You can get a really, really good head start if you learn all of this. Anybody else? Okay. Thank you for your replies. So, deploys on Friday is kind of a taboo among majority of software developers and teams these days. And why is that? Because you probably don't want to fix bugs and critical issues after the deployment on Saturday or Sunday. Hence, if you have something to deploy, you'd rather better wait until Monday, right? So this is the common sense, and that's what common sense tells you, and that's what people do. However, if you listen to my talk today and start applying the techniques that I'm going to talk about, you're not going to have to worry about it, at least not often. So maybe that will happen like once per year, once per 2 years, but that's all. It's not going to happen very often. So, as you already know, I'm currently head of engineering at Rider Capital. I'm ex-Pivot, so everybody who works at Pivotal calls themselves pivots. That's because we're really kind of people who are driving change. So I'm a change driver. I'm currently implementing all of the stuff that I'm going to be talking about today at Rider Capital. And I have tons of experience in programming. I've done all of the different stuff. I've done microservices, I've done different architectures, I've done event-driven architectures, I've done mobile development, back and front end. I've done desktop and also a little bit of robots and stuff. And also blog at TD Fellow about coding and quality and professionalism and other topics. So you're welcome to check it out. And before I start, I want to tell you just a short story that I've encountered personally in Germany of an embarrassed CEO. So it was a startup that had a very, very successful product in Germany, and they wanted to scale up and go into US market. However, the CEO didn't want to do this yet because their engineering team was delivering results not very nice, and he was embarrassed because every time they have deployed to production, there were critical issues that they had to fix, and every time they fixed one or two new bugs, there were further and further bugs after that. So there were always a string of fixes 1 or 2 weeks after the production release every time. So that's why they were holding back on taking their business further. Even though business was successful, product was successful, engineering wasn't. And if you don't want to get into this situation, let's actually dismantle and see why these things could happen and how it can get to this situation. So I want to tell you just a little bit about nature of software development in general. So software development and software engineering is not like civil engineering or similar disciplines, because we don't plan ahead for a few months for the next 5 years of a project, and we execute a project flawlessly, and we can call it that done, and we just do maintenance mode. We don't work this way because the software development and software engineering and software itself is supposed to be soft, which means that it can be changed easily. It's a foremost and first value of the software development, that you can make changes over and over again quickly. That means that if you have a huge plan for what you want to do, it's kind of defeating the purpose. You're not using the value of software. And any plan will change if you have one, because That's why businesses build software, because they want to make changes very quickly. So what do we do instead? Because of this, we develop any software one small step at a time. So we develop feature by feature, epic by epic, layer by layer. The result of this is that we usually start from something simple, foundation, and we build on top of it one small iteration at a time. However, at some point, the foundation is no longer good enough for what we are building. So it's like we're building a big building on top of the foundation of certain size and certain quality, and as we want to add more and more floors, that foundation is not good anymore. So what do we need to do? We need to strengthen the foundation, widen it, and make it better. And that's this foundation is our design, is our architecture, is our test suite, all of these components of software. Now, if you want to improve them, we have to do certain things. However, most of software teams don't do them, or don't do them well enough or enough of them. And the result is that the complexity of the foundation is growing over time, because you're not explicitly making the changes that you're supposed to make. You're making them at random, without a good plan, without good technique and good practice. And the result of this is that the complexity of software is growing over time almost uncontrollably. Every time you add a new feature, every time you introduce a change, every time you even fix a bug, you're slightly increasing the complexity of the software system. And the result of that is that the complexity is kind of exponentially growing. And why complexity is bad? Because complexity is actually the source of bugs. What is preventing us from deploying at any time that we want is that we will have critical bugs. But why would we have them? Like, where do the bugs come from? Besides the issues when somebody doesn't have enough skill or doesn't have enough knowledge, usually bugs come from communication problems. And by the way, majority of software developers, they're really good developers and they know what they're doing. So majority of bugs, like 95% of them more, don't come from lack of skill or something else. They actually come from miscommunication of one or another sort. And sorts of types of miscommunication that we have is when you have collaboration issue between the business and engineers, for example, or maybe a business and their customer. That's one of the sources of bug that you have. Another source of bug that you have is when you misunderstand something in your code base, and then you try to make a change, and it seems like it's working, and then at a later date when you deploy that to production, suddenly you have bug report because there was something that you've misunderstood. And that misunderstanding is essentially a misunderstanding between the previous author of that code and you. And by the way, that previous author can be you yourself. So it's a situation where I write some code, 3 months later I look at this code and I understand it slightly differently than it was intended. And that misunderstanding could lead to problems. And finally, the third type of misunderstanding is implicit dependencies that you have. For example, let's say that you have a piece of code, a module responsible for certain thing for orders over here. And then you have some logic in different module also responsible for how orders is handled in different place. And the result is that when I need to change the behavior of how order processing is working, I would change that module because that's an obvious way to do it. That's where you go for these changes. And I wouldn't know because there's nothing in code that tells me there's another place that I also need to change. And the result of this is usually these inconsistencies in software behavior that we consider also bugs. And the reason for this is also complexity, because by trying to accommodate for the complexity of software in a single software package, we can't accommodate it. We have to do something in order to reduce that complexity so that we don't have these bugs. Also, another problem with complexity is that it slows us down constantly. Because the complexity is ever growing, that also means that the development teams will slow down over time. Which means that if you started a new blank state code base today, it might take you 1 hour to complete a simple feature. But then fast forward, maybe 6 months from now, suddenly the same type of feature, the same size of complexity will take you 1 week maybe, or maybe 3 days. However, if you actually fight complexity, if you take care of your foundation and you constantly rebuild it and adjust it for the size and complexity of the software that you're trying to build, it should still take 1 hour. If it took 1 hour 6 months ago, it should really take 1 hour now. And maybe where we allow some time slippage is 5 years from now, it should take 1 hour and 20 minutes or 1 hour and 30 minutes. So this is the rate at which it should really grow. But unless you do something about complexity, it doesn't grow that way. It grows exponentially. That's what I'm saying. Like if I were to graph them, if you don't update foundations as you go, you have really, really fast start, but then it plateaus and you become slower and slower and slower over time until you grind to stop and halt. But if you do update foundation as you go, you will start not as fast, but steady, and then you'll keep that steadiness over in infinity throughout your project. The interesting thing about these graphs is that you can try to combine them and see that you could potentially start very quickly, and then when you start slowing down, you switch to another mode of operation and continue steady. However, that has a cost and risk, because switching between these two modes of operation is really tough, since when you're so fast, suddenly you need to start taking care of your foundation and start improving on it. There is a certain amount of technical debt, as they call it, that you would need first to work through. So there's initial investment that you need to make, which means that your speed will drop almost to zero, or like will be cut by 60% in order to get that out of the way. And then you can start doing a steady pace. And the risk with this is that the business might not like it. So you have to get some kind of permission to do it, because you'll have to stop the feature delivery or stop it partially. And the result of this is that business will say, okay, how much time do you need? And you might say, let's say 2 weeks, and they give you 2 weeks, hopefully. And then what happens is that you will probably have underestimated the problem and how much investment needs to be done to switch to another mode of operation. And the result is that you'll be over time, and the business will come in and say, just stop it, don't do it, and you have to revert. So this is the risk of making these kind of changes. So the best way and less risky way is to actually start this way, always. Okay, so another important thing is that you want to have, if you want to be able to deploy on Friday, is a damn good test suite, and I'll explain why. So this complexity that we have and the foundation that we want to take care of, every time we want to make any sort of change that reduces complexity or improves how many features we can put in our software and how easy they are to implement, you need to refactor or change the structure of your code. You need to change the architecture. You need to improve it and evolve it over time. However, it's really hard to do if you don't have a good test suite, because then how do you know that you haven't broken anything? And when I say good test suite, I actually mean damn good test suite, which means that I want to have 100% test coverage. Now, the test coverage is a really interesting metric, because most people misunderstand what it means. Let's say that somebody have seen test coverage tools, and what they calculate lines of code that have been executed during your test run. Or maybe, if they are more advanced, they count how many branches your code has entered during your test suite. However, they don't actually check that you are verifying the behavior, because you can write a bunch of tests that execute your code, but don't check anything. So your actual test coverage is 0%, but any tool will report 100%. So the test coverage that I'm talking about is really a coverage of knowledge encoded in your system. I'll explain what I mean. As a programmer, as a developer, your job is actually to take the knowledge of other people, and maybe your own knowledge as well, process it and find solutions to the problem, so generate more new knowledge, and then encode that knowledge into your software system by writing source code. So source code is only a representation of this knowledge. So when I say 100% test coverage, I mean the coverage of that knowledge that was encoded in the system. Of course, 100% is a goal. Like it's rarely exactly achievable and also non-practical, because there is important code or important knowledge and there is unimportant details. So for example, unimportant details sometimes may be left uncovered. Of course, all the important and critical stuff needs to be 100% covered. This test suite is interesting because it gives you a really, really high level of confidence. It gives you the confidence to make a deployment at any time you want. It gives you the confidence to change your code and be sure that it works like you want it. It makes you the confidence to make changes to your architecture and be sure that after you made these changes, everything still works. So this is really, really good. And if you have a test suite like that, you'll have only 1 or 2 real bugs per year. And sometimes you'll have like behaviors that don't exactly behave like somebody wanted, like for example, a customer. But you wouldn't consider that a bug because from your perspective, they behave exactly like you want it. So when something behaves like you want, you can't consider that a bug. It could be a mistake at the previous level, right? At the level of thinking what you want to do even. But if something doesn't behave like you want, or not like you expected, that's what the bug is. And this very rarely happens when you have a good test suite. So how do we actually get the test suite like that? There are 2 techniques that are usually very good when in combination. One is called test-driven development, another one is called acceptance test-driven development. And they're actually the same, almost the same thing, but on different levels. So test-driven development is applied to so-called developer-level tests. These are the tests that are testing a single unit of a system, such as the class, function, module, method, or something like that. And then acceptance test-driven development is applied at the level of business, where we are testing whole features. So let me talk through test-driven development. What's its essence? In essence, every bit of knowledge that you have in a system should have had a failing test at some point. So you don't introduce the knowledge into the system unless you have a proof that the knowledge is required. And your failing test is a proof of this. And you achieve this by following a simple red, green refactor cycle, which means that you write a failing test first. Sometimes that actually means writing code that doesn't even compile because you're trying to call functions or create classes or do whatever, render components that don't exist yet. So obviously it will not compile and not run, not pass. And then once you have the failure, you think what is the simplest implementation that you can have to make it work. And the emphasis is on simplest here because it's very easy by accident to implement more than the test requires. And you say, why would I not implement more? Well, because then the test-driven development breaks and doesn't give you 100% coverage test suite. The issue with implementing more than is necessary for every single test that you have failing is that you will leave holes in the test suite that don't test extra behavior knowledge that was encoded during the last cycle. So the idea to implement the simple solution first, then refactor it to make it better. Let's say change the structure, change names, and so on. Also refactor your test suite because sometimes you'll have duplication problems in your test suite, so you should refactor them as well. And then you start the cycle again, and you do it by looking at your code that you have after every green and refactor and asking yourself a question, what is still missing? What knowledge haven't I encoded yet? And then you write the next test to prove that that knowledge isn't there yet. And by the way, sometimes it passes. Sometimes you find out that it's already working the way you want. And you repeat that cycle over and over again until you're done. Essentially, the way that I work, I usually go into that cycle for 15 minutes, 30 minutes, sometimes hours at end. And then when I think I'm done, I just open the browser, open the application, and I see that everything works in the end. So I don't check in between how my application works, actually. I might still do some CSS changes later because if you have UI changes, and you use TDD, you have perfectly working software, but UI will look horrible because you didn't worry about it. And that's actually good because then you can separate different phases of development, which means that you can focus on what you're doing. So you can focus on making it work correctly, and then you can focus on refactoring, and then you can focus on making it look right. Now, acceptance test-driven development is kind of similar to test-driven development, but it's a bigger cycle. It's a cycle around your whole application. So here, together with business, the developers should sit down and write so-called acceptance criteria. They could be in Gherkin format or something else, doesn't really matter. But what matters is that they should be binary, which means that if somebody were to run through these steps, they're unambiguous, so somebody can run them, and also program can run them, so you can automate them. And they have binary result. Either it works or it doesn't. Because then it's really easy to accept the features and accept the changes in the software. So for example, as a program manager, if you have acceptance criteria like that, when you want to accept code from developer, it's really easy. You just run through the acceptance criteria, several scenarios, and if everything worked like it says, you're done. Except for maybe like something doesn't look right in UI-wise, you can provide feedback, but in terms of behavior, that's done. Now, if the tests are a bit fuzzy, where you could say, oh, it kind of works, but kind of doesn't, that's not a good acceptance test-driven development test. You should make it really binary. Also, important thing when you use acceptance test-driven development is that you don't write your developer tests before you have a failing acceptance test. So then you first encode your acceptance test in your favorite testing framework, or you automate Gherkin. And then you run it, you confirm that it does fail, which proves that you don't have that functionality yet on a bigger level, on a business level. And then you jump into inner cycle of test-driven development, which is red-green refactor, and you implement just enough of the functionality on the developer level to make this failing acceptance test pass. Then you confirm that it does pass. Sometimes it doesn't because you forgot something, and you'll think, what did I forget? And you find another module of the system that you need to change. And then finally, when it does pass, you enter the refactoring stage, the bigger cycle. And this is where you think not about like names of functions or how one function or class or file looks like, but you think about the whole system. Like, was this change easy to do? And if it wasn't, ask yourself, why wasn't it easy to do? How would the structure need to be so that this easy change that I've just done would have been easy? And you made this structure change. So this is a bigger refactoring. This would be change in architecture. And then you continue the cycle. You choose the next acceptance test. You write it, it fails. You make it pass with inner TDD cycle. And then you look for more refactoring opportunities. I've been talking about refactoring quite a few times already, so I want to make sure that we understand what it is. So refactoring is the change to the code structure without changing the behavior. That's interesting because the symptom of this is that when you make a refactoring change in your software, you can run all tests and they should still pass. And the interesting thing is that a significant amount of people think that they are refactoring, but they are actually rewriting something. And the result of that is that they make the change they wanted to make. Usually takes them several hours and sometimes several days. And then they run the test suite and 30% of their test suite fails. And then they struggle for the next 2 weeks trying to make everything work again. They have to spend time in debugger. They have to add printouts and console logs and everything into the software, finally finding all the little bugs. And then they deploy the system and there are still bugs after that. So this is not refactoring. This is called rewriting. And it has its own place in different cases. But in case you want to do refactoring, that should be a quick change. I'm talking about 2 to 15 minutes change. It's a small little step that moves the system from green state working to green state working. And by the way, after each refactoring, you can deploy without any problems, or should be able to. Refactoring is for things like when you have something that is not very readable and you want to improve readability, you want to improve names, you want to change a structure inside a file, a structure of multiple files, you want to combine two different functions together, you want to extract functions from existing function or method. Perhaps you want to combine classes or extract more classes or modules, whole modules of the system. So this is the level of refactoring that you have. And you do it when you see something that's hard to understand, or you want to make it easier to make certain changes into the system. However, refactoring could break things, right? So because when you refactor, this is supposed to be not making any changes to behavior. But what if you did make change to behavior on accident? Maybe as any person, one can make a mistake and make a change that was unexpected, unintended. So refactoring can technically cause bugs really easy. So if you don't use automated refactoring software, even that could cause bugs. Or maybe there was some distraction in the middle of refactoring, or just maybe code wasn't really easy to understand, so refactoring has failed because of this. And you deal with this thing by having that amazing test suite I was talking about. So if you have 100% test suite coverage, you run it, and you know whether you broke something or not. So every time you made a change, you run the test suite. If it's green, you're done. You don't have to think about it. You can just jump to next refactoring or move on to the next piece of functionality that you want to implement. However, if it fails, you know almost precisely what is wrong. Because if the failure is in a unit test level, which it should be at this point, at the developer test, it points you almost directly to the part of the code that is wrong and also what is wrong about it and in what scenario. And then you have to just read the code, understand what happened, maybe fix it immediately, or there is an easier way. You can also just undo the refactoring. Especially if you make comments into your version control system between your refactorings, then it's really easy. You just undo whatever you have in the working directory, and you're done. And then you can either attempt refactoring again in a different way. And now I want to talk about something else, which is a different twist on refactoring. I call it continuous refactoring. The problem with refactoring is that it could take a lot of time. So for example, let's say that you look at the incorrectly structured code and you think, okay, I really want to make it better. Like the last time I had to implement a feature here, it was really, really painful, and I want to really make it better. Now, you think to yourself how much time it would take, and maybe even business or product owner is asking you, so how much time you want for this? And you say, maybe 3 hours. And these 3 hours could be granted, could be not. But this is like a big question. Could 3 hours or even 3 days, if it's a larger refactoring, be granted for such operation that doesn't bring business value, at least not obviously from business and product perspective? So here the trouble is that you have to even ask the question to do the right thing. But what if that refactoring took you 10-15 minutes instead of 3 hours, or maybe 1 hour instead of 3 days? And you can get that. The same refactoring can take one person 10 to 15 minutes that other person needs 3 hours for. Why? Because refactoring is actually a very, very interesting skill that needs a lot of deliberate practice to train. And also it has a lot of supporting tools that one need to learn as well and to be proficient with them. So actually you can be beginner refactorer, you can be advanced beginner refactorer, you can be proficient, you can be confident, you can be master of refactoring. So it's like its own kind of skill. And it takes usually a year or two of deliberate practice every day in refactoring to learn it to a really, really good level where you can turn 3 hours refactoring into 10-15 minutes refactoring. But if you had this, then you wouldn't even need to ask the question whether you want to perform the refactoring or not. You would just do it. Because if it's so easy to do, you would just do it and you would just improve the system. And if you do it every day, let's say that every hour you spend 2 minutes refactoring, or every day you spend half an hour refactoring, then the system will improve over time further and further and further. Okay. Staying in the bounds of continuous stuff, I want to talk also about continuous integration. So the modern definition of continuous integration is actually talking about build servers. You know that the definition where when we talk about CI, we mean Circle CI or Jenkins or Travis or Concourse or whatever build server you have. But it's actually not the practice itself. The practice itself was there for a very particular problem. And the problem was that when you stay in development mode for a long time on your own branch or fork or whatever, and you're not integrating and not merging back with the mainline with other developers in the system, you'll have in the end, when you do want to integrate, merge conflicts and very slow feedback. So let's say that you do code review for something that was in progress for 2 or 3 weeks, how much comments you're going to get? Like hundreds potentially. And the problem was solved with continuous integration, which meant integrating the code continuously. That means merging things together from developer to developer into a single branch called mainline, maybe every hour or so, or maybe every few minutes or so. Maybe after every commit, you would merge them. Another thing is that if, for example, if your company adopted CI, but your feedback cycle is still slow, it's still weeks, that means it didn't really work. It's not really adopted, because the purpose is to get the result. Result is that you don't have to worry about merge conflicts, mistakes as a result of them, and slow feedback. Now, the problem with merging the changes so quickly is, where does the code review stand here? Like, how do we do code review if we merge every 5 minutes? We can't, right? Well, there is a solution for that as well. What if you could get code review comments instantly? What if you're writing the code there, right, and you get a comment, oh, this name of the function it's hard to understand, let's try something else. Or you write some more code and, oh, this if statement is starting to be really gnarly. What do you think we extracted it to a function? Or you can get that instant code review if you pair program. So this is really a way to replace code review and PR process if you do proper pair programming. And there are, though, few problems with pair programming, is that people in different organizations actually get tickets and features and work assigned to them personally. Let's say that I'm a developer and there's another developer, Oliver, over there, and I have the ticket assigned and Oliver has another ticket assigned. And let's say that Oliver needs my help and I would like to pair with him, but then I think, oh, well, but if I pair with him, I spend time there, I don't spend time on my ticket, and then my manager will ask me, hey, so why you're working slowly? Like, because I help other people, but still there will be the question. So I feel kind of reluctant. I kind of feel reluctant to pair. And that's not good. And the solution for this problem is really easy. Don't assign tickets to people, assign them to teams. And have the team decide how they want to pair, solo, mob on every single ticket, and so on. And preferably they'll pair. Another problem is that a lot of developers say that they don't like pair programming. They tried it and they don't like it. Well, usually when they tried it with somebody else who never done it before. And the problem with that is that pair programming is also like refactoring a skill. So it's a skill that you need to develop over time for like a year or two of doing it every day. And if you try to pair, you never paired before, you're a beginner, and another beginner, you just don't know what you're doing. I can tell you what is proper pair programming looks like. It's, let's say, me and Oliver, we just talk about the problem. We exchange ideas, we ask each other questions, we give each other feedback, and we just bounce ideas from each other and constantly talking about the problem at hand. And the code is just gets written on side almost automatically. Yes, somebody types on the keyboard, one of us, or we change the keyboard, who controls the keyboard. But the code just is a side effect of that fruitful discussion. That's how real pair programming looks like. And if you try to pair program with somebody who knows what they're doing, you would probably love pair programming. And finally, the problem is that somebody says that they can't work with people so well, or they don't want to work with people too much. And that's understandable. However, I'm linking to the report there. It's a research about the importance of social skills in the market. And just to summarize it to you, to achieve any great thing, you need multiple skills at the great level. And most likely more than one person can actually be at a great level. So if you need multiple people excelling at different skills, then they need to collaborate, which makes this kind of skills of collaboration almost required. And that means that you need social skills. And the best way to get social skills is to work with other people. The more, the better. Right? And by the way, if you're excellent with 1 or 2 technical skills, actually the social skills become your multiplier. Because if you're already excellent, what does it take to get 2 times better? Well, years and years more of practice. But what does it get to be 2 times better if you can partner with another person with different set of skills? Well, just a little bit of social skills, and you can be twice and thrice more effective together. Finally, about peritation, there's a problem when you start pair as a team, is that people find favorite pairs and they just keep pairing with them. The issue is that this will create knowledge silos of 2, not 1, it's better than 1, but 2 knowledge silos is still not good for example, so lottery factor and also for efficiency. And we want to break that silo, and how do we do that? We start rotating pairs every day, for example, every week. That means forcing people to say, okay, I worked on this ticket enough, you go on, I'll join somebody else, and somebody else joins you, to swap pairs. The interesting thing about this is that you might say that there is a problem with efficiency because you need to do knowledge transfer every day, let's say in the morning or every week on Monday, so that you can work with somebody else. But the interesting thing is that knowledge transfer is also a skill that you get to train, and you can get better at it. So if it takes 1 hour in the beginning to transfer the knowledge in the beginning of a day, then if you do it for a long enough time, it will take you 5 minutes or 10 minutes to transfer the knowledge, and it will be very efficient. And when you do this knowledge transfer every day, what you get is called knowledge pollination. That's where knowledge about your system, about your product, just basically spreads inside of your team. And if you do any cross-team activities, then it spreads throughout the organization. It's really good. Finally, live and master. I'm going to be quick because I don't have enough time. If you combine all of these things I just talked about, you can actually just push always to master. By the way, I should change this to main because now it's main. You live on main, which sounds a bit weird. Basically, trend-based development. So what you do is that you don't create branches and you push to branches, have them pull requests and whatever. Instead, you just push always to your production branch, to master branch. And if you do that, you can also actually just deploy that to production almost immediately after all your tests pass. Of course, there are a few more things that you need, like feature toggles and good monitoring and automatic rollbacks in cases of critical failures. But these are quite easy to get once you know what you're doing. And I want to conclude is that if you take any single practice out of these, and by the way, these are all practices, most of them are from Extreme Programming, and you can get that book with the link that I pointed. If you take them as isolation, they're kind of, yeah, good practice, but not great, not super. It's like there are other alternatives. But if you take them all together, they kind of multiply each other. So if you're good at all of these practices together and you apply them, you're getting benefits like 300, 400, 500% improvements. For example, I've been on a team where we deployed 24 times a day to production. It's pretty good, right? And I'm talking about 1 pair. So we had 3 pairs, so you can imagine the number. Okay, I'm going to open up for questions.
Wonderful, that was great. Thank you very much, Alex.